Hello, hi, good evening to my dear students. I welcome you all for the topic called relation between E and H, electric and magnetic intensities in uniform magnetic field or uniform plane wave in the background. Okay. Before we are going to the detail about the topic, let us first see what is uniform plane waves. The amplitude of the waves should be the same at different times at the plane wave, where the waves started spreading outwardly, what we call uniform plane waves, which means when the energy is emitted by a source, it expands outwardly from the source in form of spherical waves. The spherical waves travel at the same speed in all directions with the same amplitude and same space, the same rate. To an observer who is very far away from the spherical waves, it looks like planar waves, what we called uniform plane waves. Okay, this is what the whole idea definition for the uniform plane waves. We are going to compare the relation between the electric and magnetic field, electric and magnetic intensities of a plane wave. Okay, let us see the derivation in detail in the following slides. As we discussed, to determine to derive the relation between the electric and magnetic field intensity in the background of uniform plane waves, we can consider uniform plane wave traveling or propagating in the direction of z. We know the Cartesian coordinates x, y, z. We are constraining these uniform plane waves propagating only in the z direction, meaning the electric and magnetic field are perpendicular to the propagation direction, which results Ez and Hz is equal to 0. But it has other components like E of x component and y component. Likewise, the magnetic field of x component, y components are there. They are not 0. Okay, so it has Ex and Ey components and Hx and Hy components. The electric and magnetic field along the z direction is only equal to 0. One more important topic is there is no variation of field components along x and y directions, meaning the partial derivative of a field variable with respect to x and y directions are 0. Dou by dou x and dou by dou y are 0. Now we are going to consider the Maxwell's first equation, del cross H is equal to Jc plus differentiation of partial derivation of density d divided by t. Jc is equal to sigma e and d is equal to epsilon e. We are replacing those equivalent values and considering this equation as it is. We know that in free space there will be no charge available to conduct electricity, through which there will be no magnetic field, which results the charge density sigma is equal to 0. So the above equation reduced as del cross H is equal to epsilon dou E by dt. We are going to consider only the left hand side. First, later we can consider the right hand side. Left hand side del cross H is equal to the del operator can be written in form of matrix derivation, which is represented here. The first column reads as Ax, Ay, Ez. The second is nothing but the partial derivative with respect to three coordinates x, y, z. The third column is nothing but the h coordinates, hx, hy, hz. We are going to determine determination of this matrix as it is. So Ax taking partial derivative on this direction minus on this direction. So dou by dou y of hz minus dou by dou z of hy. First this one minus this one. Next minus ay, instead of that I am taking plus ay. So I am reversing this partial derivative direction. First I will take this, next this, which results the negative direction, negative value in the minus ay into minus become plus ay. So plus ay, I'm taking derivatives on x and y directions. Finally, plus az, derivative on other two directions. As we discussed earlier, there are few parameters set to be 0. Nothing but Ez, Hz, partial derivative with respect to Hz, partial derivative with respect to x and y directions are 0. By applying those conditions on this equation is reduced as like this. Now we are going to consider this equation. to compare with this equation. So I am rewriting this equation again here. Del cross H is equal to this one is the derived one. Del cross H is equal to epsilon dou E by dou T is an already known one. Wait a minute. It's already known one. I am going to consider the value of E component. E is nothing but EX, AX plus EY, AY plus EZ, AZ. As I said before, there are few parameters set to be 0. So EZ is equal to 0 here. By substituting the value of E is equal to 0, we are getting right hand side values are equal. Okay, so AX minus AX dou HY by dou Z plus AY dou HS by dou Z, which is equal to this value, which is replaced here. Epsilon dou E by dou T. This E value is replaced as EX AX plus EY by Y. We know that E is equal to 0 as at the preset preambles or preset conditions from the planar wave background. I'm repeating the same equation what we have seen in the first page. From this we are going to simplify a few things. Now I'm going to compare only the coefficients of AX on left hand side along with right hand side. Consider on left hand side the coefficient of AX is nothing but minus dou HY by dou Z is written here. Likewise the coefficient of left hand side, right hand side has been derived here. Likewise I am going to calculate the coefficient of AY on left hand side and right hand side as it is. Now here I am replacing or I am shifting this negative value by multiplying the negative on this equation. I am getting a positive 1. The positive 1 becomes a negative 1. I'm considering this as equation 1, and right hand side there will be no change. So I am keeping as it is. I am considering this as equation 2. So finding the scrutinized values or finding the solutions for these two equations help us to find the exact or the relation between the electric and magnetic field intensities on a uniform plane wave. Okay. To find the solution for this equation 1, I am going to consider the E is as the function of Z minus Ct. Now I am going to differentiate this EX with respect to T, partial derivative. So dou EX by dou T, as like in the right hand side value, by differentiating or taking partial derivative on two variable things, we have to consider dou function, dou f of Z minus Ct by dou of the augmented function Z minus Ct, again differentiating this augmented function with respect to the original derivative. Okay, so dou of Z minus Ct by the original derivative is T is considered as T here. There will be no change in this rational value, so I am keeping it as it is, the numerator and the denominator value. We are considering here partial derivative with respect to Q leads us minus C into 1 T divided by T. T with respect to differentiation of T becomes 1. So minus C into 1 becomes minus C. Taking equation 1 here again. So partial derivative of Hx by dou Z, which is equal to minus epsilon. Instead of this dou Ex by dou T, we are having that equivalent value here. We are replacing this equivalent value in this above equation number 1. This is nothing but this value. By multiplying this minus epsilon with this minus C, I am getting epsilon C dou F by dou of Z minus Ct. Now I am going to consider this particular numerator denominator value like dou F of Z minus Ct by dou of Z minus Ct as F prime for some sake of simplification. Finally end up with replacing this particular rational with this simplified F prime. This results here. Dou Hy by dou Z is equal to epsilon T F dash. I am rewriting this above equation to achieve our relation. So keeping this partial derivative of Hy on left hand side, taking this partial derivative with respect to Z, the derivative on the right hand side as it is. To remove this partial derivative, I am adding integration on both sides. Integration and differentiation getting cancelled on left hand side, integration add up on the right hand side as like this. Let me consider finding what is equivalent to F dash. For that I am considering dou of F of Z minus Ct by dou Z, which is equal to, by differentiating this, I have to augmented partial derivation. So dou f of z minus ct by dou of z minus ct, again augment derivative, dou of z minus ct by dou z. This is nothing but f prime or f dash, and dou of z minus ct by dou z results to 1. The ct will become constant, so it will go 0. We have dou z by dou z reaches to the value of 1. From this we are calculating what is the value of f prime equivalent. So f dash or f prime is equal to dou f by dou z. I am replacing this f price value in the above equation. Is like this. I am cancelling the cancelled or equivalent parameters dou z and dou z, integration with differentiation. Finally end up with hy is equal to epsilon c f of x z minus ct. Hy is equal to epsilon c, the f of z minus ct is nothing but the considered solution. Considered solution or assumed solution. So we are replacing this f of z minus ct as ex here. We can go to the next page. I have rewritten the same here. Hy is equal to epsilon c ex. I am rewriting it in a suitable way or in such a way that we are going to derive that relation between the electric and magnetic field densities. So taking this hx on right hand side and the epsilon c on left hand side, it will be written like this: ex by hy is equal to 1 by epsilon c. Now I am replacing the value of c in terms of permeability and the permittivity of free space. So the c's can be replaced by 1 over square root of mu and e, mu and epsilon. I am rewriting this as like this: square root of mu epsilon by epsilon. Simplifying it results to ex by hy is equivalent to square root of mu by e. You can consider this as star 1 or first part solution 1. Likewise, I am deriving the solution for the second part by means of magnetic field. For that, I am taking that second equation. To find the solution for the second equation, I am considering Ey is equal to f of z minus ct. Taking this Ey with partial derivative with respect to t, and it leads to f dash minus c. Replacing this dou y by dou t value in this above equation leads to this particular equation: dou hx by dou z is equal to epsilon f prime of minus c. Multiplying all these will leads to this equation. I want to remove this differentiation by means of integration. So taking differentiation on both sides. So differentiation integration getting cancelled on left hand side. On right hand side, this integration is getting added in the equation. Now I am going to consider what is the equivalent for this f dash as we derived in the first part. For that, I am considering dou f of z minus ct by dou z is equal to dou f of z minus ct by dou of z minus ct into augment derivative dou of z minus ct by dou z, which leads to f dash into 1. I no need to explain again, which has already been discussed in the previous part. Finally, I am replacing this f prime value in the above equation, getting this value and cancelling the equivalent values, dou z in the denominator and dou z in the numerator, and the integration and differentiation getting cancelled. Finally end up with hz is equal to minus ce f of z minus ct. Now I am getting hz is equal to minus c epsilon ey. From this, now I am going to rearrange, or we are going to rewrite this equation in such a way that you are going to get the relation between the electric and magnetic field intensity as like in the first part. So Ez by Hz is equal to minus 1 by Ce. I am replacing the value of C in terms of permeability and permittivity as like in the previous part, and simplifying it, finally end up with the relation between Ey by H is equal to minus square root of mu by E. This is nothing but the solution part number 2. From the solution part number 1, we are considering Ex by Hy is equal to square root of mu by E. From this, we are calculating Ex is equal to Hy into square root of mu by E. Like that, we are taking the solution part to Ey is equal to minus Hx square root of rational between mu by E. We know the electric field parameter, electric vector E is equal to Ex Ax plus Ey Ay. When getting modulus of that electric vector, which is equivalent to square root of Ex square plus Ey square. Substituting the values of Ex and Ey, what we have taken here in this equation, we are having hy square mu by E. By squaring the above equation, the square root will cancel each other. The square root of mu by E will become mu by E, as like in the second part also. Minus will get minus, into minus get plus. From this, we are simplifying this equation as like this. Now we are again going to consider the latter part, magnetic field part. H vector is equal to HSAX plus HYY plus HSAZ, as like we consider EZ is equal to 0, H is also 0, so we don't need to worry about the third term. So the modulus of the magnetic field vector is equal to square root of Hx square plus Hy square. We are using this value in this above equation. We are replacing the square root of Hx square Hy square with this equivalent value modulus of H vector in E vector formula. So E vector is going to be replaced as square root of mu by E into H vector. By taking this H vector from right hand side to left hand side, we are taking the ratio between the square root of modulus of E vector by H vector is equal to square root of mu by E is nothing but the required intrinsic impedance or characteristic impedance eta. This is what the required relation between the electric and magnetic field intensities and the background of uniform plane wave which is traveling on any medium.